Hey, AP Chemsters, this is Mrs. Vanderwally, and obviously I'm not here today. I'm a little under the weather. So, what I'd like to do is finish up our problem sets for section, I don't know, 12.6, which was the proposed mechanisms, and then go on into your notes and hopefully finish them off today. As always, jot down any kind of questions you might have, and I'd be happy to answer them when I'm able. So, why don't you pause this? And when you get your notes ready, then come back. Okay, problem number 18 says an environmental concern is a depletion of ozone in the Earth's upper atmosphere, where ozone is normally in equilibrium with oxygen gas and an atom of oxygen. A proposed mechanism for the depletion of ozone in the upper atmosphere is shown below. So here you have step one. You having ozone, the O3, and then there's this chlorine atom. You don't normally see chlorine by itself. What has happened in the atmosphere that chlorine is from the chlorofluorocarbons, which was in aerosols, and that's why they were banned, because they become chlorine free radicals, is what they call them, a chlorine atom in search of electrons. So the ozone and the chlorine then will react to make oxygen gas and this chloroxide there, monochloromonoxide. And then the step two is this chloromonoxide will bump into another oxygen atoms, and this chlorine is all by itself. You make oxygen gas again. So it says write a balanced equation for the overall reaction represented by step one and step two above. This is just like Hess's law. So cancel out whatever you can that you find on both sides of the reaction. So here's your overall reaction. So ozone bumps into another oxygen atom, a free radical, and it makes two oxygen diatomic elements. And so this is a depletion of ozone. So if we can eliminate that chlorine in the atmosphere, we can preserve our ozone and hopefully protect our UV or the UV radiation from getting too bad. So it says clearly identify the catalyst in the mechanism above. The catalyst is something that is not part of the reaction but is consumed and then made again. That's why it doesn't run out. That's the danger of having even a little bit of chlorine in the atmosphere, is that it keeps making it again. It uses it and makes it, it uses it and makes it. So chlorine in this case is our catalyst. So here it is being consumed, and here it's being made again, regenerated. So it is definitely the chlorine atom that is our catalyst in the above thing. It is consumed in step one, and it is a product in step two. And it says describe the intermediate in the mechanism above. It's the opposite of a catalyst. It is what is produced in step one and then consumed in step two. So it too does not show up in the overall balance equation. So that would be the ClO. I'll use green for that one. Oops. Again, the intermediate, it is produced in step one and consumed in step two. Okay, so part D says if the rate law of the overall reaction is found to be rate equals the constant times ozone times chlorine, determine the following. The overall order of the reaction. Well, the overall reorder is just add up the two exponents. So ozone to the first, chlorine to the first, so the overall reaction is 2. So the appropriate units for the rate constant K, well, rate would be something like molarity over, or moles per liter times seconds. Let's just use seconds because that's a common one. And that's equal to K times moles per liter over moles per liter. And if you get rid of one of the moles per liter, and now we have to get rid of the other one, so we have to, in a sense, flip it. So K is equal to L over moles times seconds. And now the last one is the rate determining step of the reaction along with the justification for your answer. So if you remember from the last blank wall, they were saying the rate, or I was saying it, not they, it's me, was saying that the rate determining step is the slow step. So let's go back. What has to be true for this slow step? It has to agree with the rate law. So is it step 1 or step 2? Which one has ozone and chlorine in it? Well, if I erase all my marks up ahead, it looks like step 1. See how step 1 has ozone and chlorine? So you have to have that effective collision between the two of them for the whole thing to start in this case. So your rate determining step is step 1. It agrees with the rate law. And how do I know this? Well, you can make a rate law for both of the reactions, both the steps. So let me erase this and kind of talk about that real quick. So here we go. So here's the rate law for number 1. And here's the rate law for 2. Okay, so which one of those agrees with the rate law from down here? And it looks to be step 1. So step 1 is our rate determining step, step 1. Okay, let's go on to number 19. All right, so if you will, go back. Well, let's read the problem. Nitrogen oxide is reduced by hydrogen to give water and nitrogen, and there's the equation. And one possible mechanism to account for the reaction is, and there's your 3 steps. So they didn't actually identify them as step 1, step 2, step 3, but there they are. And what is the molecularity of each of these 3 steps? Show that some of the elementary steps is a net reaction. And that's, again, the Hess's law. But to answer the first part, let's jump back into our notes. Down here, whoops, was it this one? Yeah, right here. Do you remember what we actually changed the definition to? So a unimolecular step is a reaction involving 1 reactant molecule. The bimolecular step is a reaction involving 2 reactant molecules. So if you change that, then termomolecular step is 3 reactant molecules. So if you made that change in your notes, I think the answer is a lot easier for problem number 19. So in the first one, 2 NOs. Well, how many reactant molecules do you have? You have 2 NO, so it is a bimolecular step. Look at the next one. You have N2O2 and H2. Is N2O2 even a reactant? The answer is no. Is H2 a reactant? Yes. You have one of them, so it's unimolecular. What about the next one? Is N2O a reactant molecule? No. Is H2 a reactant molecule? Yes, you only got one of them, so it's another unimolecular. So the first one's bimolecular because you're using 2 NOs, which is a reactant. And then the next 2 are unimolecular because it only has 1 H2. Then it says, show the sum of these 3 steps, elementary steps, is a net reaction. So let me write on the board real quick. So this is a bimolecular, this is uni, and this is uni. Because here you have 2, 1, and 1. All right, so now it says show the sum of the elementaries is the initial one. All right, so let's cut out anything like in Hess's law. Looks like these 2 things can cancel out. Looks like these 2 things can cancel out. And I think that's about everything. So we had 2 intermediates in this one. So here's your 2 NO right here. Plus right here is 2 H2, and I'm leaving out my gases, I'm sorry. Yields 1 nitrogen and 2 waters. Ta-da! All right, let's do problem number 20 next. All right, it says the balance equation for the reaction of the gases of nitrogen dioxide and fluorine is blah, blah, blah. And here's the experimentally determined rate law. There it is. And here's our suggested mechanism. They said, is this an acceptable mechanism? If so, does it satisfy the 2 requirements? So, all right, what's requirement number 1? If you go back in your notes to the page I was just at, it says a sum, I'm right here, right here. So the sum of the elementary steps, hang on. Sorry, I had to sneeze and blow my nose. You didn't want to hear that. All right, so it says a series of elementary steps that must satisfy the sum of the elementary steps. Here we go. Must give the overall balanced equation for the reaction. The mechanism must agree. Here we go. The experimentally determined rate law. Again, number one is just using Hess's law. And number two, you're looking at the slow step and does it agree with the rate law. So let's go back to the problem. All right, so does it satisfy? Let's do number one. Let's cancel out things that we can cancel out, and let's check out to see if Hess's law works. Ready? So here we go. What can I cancel out? Oh, looks like F's can cancel out. So when I put it all together, it looks like I have two NO2s from here and here, plus one F2 makes two of these puppies here. Here we go. So yes, it does. Now what's the next one? So they tell you that the slow step, the rate determining step, is the first one. So we can express that rate of the slow step here. So rate is equal to the K of NO2 and F2 here. So I'm using this over here, and hey, look up there. It's the same thing as what they experimentally determined. So that would be the correct answer. I think that is it for now. We have covered those three problems. Make sure if you have any questions, jot them down. Maybe even email me if you need to. And go ahead to the next one, and that will be the notes for 12.7. See you soon. Bye.